So this is the last, if I'm not mistaken, this is already the, no, this is the second to the last slide for midterm. The interpretation of the batch reactor data and a greater bulk of the unknowns later on that you will have to answer concerning problems in reaction engineering will be dependent on this interpretation of batch reactor data. So the interpretation of batch reactor data is divided into two main groups. And the first group will be that for constant volume batch reactor. Now we will have a separate set of equations for variable volume batch reactor. So in this case, it's constant volume batch reactor. Now, under the two, so we have two divisions here. We have constant volume and variable volume, and each of the divisions that we're going to look into in terms of interpretation of batch reactor data, we're going to use two manner of interpreting the data, the experimental data. The first one, and which is actually the most often used method, is the integral method of analysis. The second one is the differential method of analysis, which is relying on a graphical technique. And that is, of course, you have to draw your curve just like what you have learned in your unit operations. So most of the time, 95% of the time, you are to interpret batch reactor data using integral method of analysis. Unless otherwise, you will learn it also later on that integral analysis will not be applicable because you've learned that it's not applicable for this particular type of problem and you have no other method to use, and that is the differential method of analysis. So two groups, constant volume and variable volume, and for each of these groups, we will have integral method and differential method of analysis. Now, what concerns integral method of analysis? So this tests a particular rate equation by integrating and comparing the predicted C versus T curve with the experimental C versus T data. So if you notice, it starts with the word tests. It tests a particular rate equation by integrating it and comparing the predicted value of the concentration given the time. This is what it meant by predicted C versus T curve, and with the given experimental data. So this is my experimental data. Is the C versus T data comparable to the one that I compared it with in terms of testing it? So I need to test my given experimental data whether it will be comparable to the predicted C versus T data. You will know how this test is done as we go along. But for now, I'd like you to really think of the word test. You're going to test whether what you guessed as the rate equation will have a comparable predicted C versus T data to the experimental C versus T data. Now, if the fit is not satisfactory, since we are testing, another rate equation is guessed and tested. So you test because you guess that this particular set of data must be for a first order reaction. So that's your first guess. Then you test whether your C versus T data fits that of a first order reaction. If it does not fit, then you have to guess another rate equation. So it's a guessing and a testing thing. But if you don't want to really guess and then test your guess, then you have to really come up with the order of the reaction and the rate constant based on a technique that we will also be discussing. So this particular method is only for simple reaction types corresponding to elementary reactions. So meaning if your reaction is non-elementary, the integral method of analysis of guessing and testing will not be anymore applicable. So take note, only for simple reaction types corresponding to elementary reaction. Now let's go to the first type of reaction. You could see a single species here. So this must be a unimolecular first order type of reaction because we view this reaction to be elementary. So if it's unimolecular, automatically it's also a first order reaction. Why is that? Because we know that if your reaction is an elementary reaction, the coefficient of your species written on the left side of your equation corresponds to the exponent of the concentration term of that particular species written in your rate law. So as a review, we know that the rate law has on the right side the rate constant and the concentration of the species appearing on the left, meaning the concentration of your reactants. Now, this concentration term or terms are raised to the coefficient of the species as it appears on the left side of your equation. So having said that this is a unimolecular type of reaction, this is irreversible, and this is elementary, it follows that its rate law is written like this. Now, from this particular rate law that you have guessed for this elementary reaction, you will process the differential equation that will allow you to solve for the concentration of A given the time. Given that you started with an initial concentration of C sub AO, what would be the concentration of A after some time T? Now you know how to handle your differential equation from your EMA 103. Then, so I will just show to you, I will just have a new share. I will show to you how you process that particular formula that you are seeing. Okay, that way later on you can do for the rest of the equations that you will also be encountering here in differential equations. So we are talking about a first order reaction, a unimolecular reaction, and you can replace this. This is your rate law. This is your rate law, and you can replace the rate expression, the negative R sub A, by the derivative of the concentration with respect to time. And you will have KCA here. Then using separation of variables then in your EMA 103, of course, you need to transfer the concentration term here on the right, here on the left, and you will have a K dt here. You transfer the derivative or the differential rather of t on the right side. This will allow you to integrate now both sides of your equation, because in terms of the variables that are appearing in your differentials, we don't have any contradictions to that because you're also integrating here in terms of Ca. So this will be integrated from an initial concentration of CaO to Ca. So we represented the initial concentration by CaO and we ended with Ca. CaO corresponds to time 0, no reaction yet, and then of course time T, the time in which your reaction has already proceeded. So if you will evaluate the left side and substitute the the limits rather, so you will have ln of Ca over CaO. And your right side would be K T. Okay, you have 0 to T. Now this one, if you would like to eliminate the ln, I'd like to transfer first the negative here. So you will have Ca over CaO, and that would be E raised to negative KT. This one, KT, you substitute 0 and T, so it would be simply KT because anything multiplied to 0 will be 0. So you have now a formula that will allow you rather to solve for the concentration of A after some time T. Of course, it's a given that you know already the rate constant K. Okay, that's for your first order reaction. Okay, a first order unimolecular, of course, elementary type of reaction. Okay, so I will go back to our PowerPoint slide. And this is the formula that I have written here. So it was only simplified in that particular board, in our board. That way you will have a specific formula that is dependent, or rather that has Ca expressed in terms of T. Okay, This is for an irreversible unimolecular, of course, first order type of reaction. Now, it could also be that you will have it, in terms of conversion. So let me go back. So you can now relate, you can change your formula, Ca in terms of uh, Ca as a function of t, in terms of Xa as a function of t. How is that? So I'd like to go back to my whiteboard. Okay, so this is it now. Now we want to express this particular expression we have on the left. There's not much to do on the right because it's just KT. I would like to express it in terms of conversion. What is that conversion? So you saw there XA. This is conversion. We refer to this as conversion in kinetics. That portion of your initial species or your species originally present in your reaction that was converted to the product. So that's your conversion. The formula that you have in the slide is negative ln of Ca over CaO. I'd like to write it here again. And you have here Kt. Okay, Kt using the limit 0 to t will simply be Kt. Now, this is your formula that allows you to solve for C sub A in terms of time. What about if I will have another formula this time, not solving for C sub A, but rather conversion? So you have to know this. Your concentration of A after some time in which the reaction has proceeded is equal to CaO 1 minus Xa. This is a very basic fundamental formula in kinetics. So you have to know this. Okay. The amount present after some time is equal to the initial amount times 1 minus Xa. So the one remaining that is of Ca after some time. So I can change the Ca here, the Ca in here to this expression. That way I will have a different formula, and that's the formula that you saw in the slide. So I will have now something like, I will have now negative ln of, I'll change the Ca there to CaO 1 minus Xa, and I have here a CaO, and I have here a Kt. So you notice we can now cancel the initial concentrations. And the formula that you have is negative ln of 1 minus Xa equal to Kt. Now, that's the one that you saw in the slide. So, negative ln of 1 minus Xa is equal to Kt. If you would like to get rid of the ln here again, so you can have 1 minus Xa is equal to e raised to negative Kt. Now, if you want a formula of Xa explicitly expressed in terms of time or as a function of time, so that would be 1 minus e raised to negative Kt. You need not memorize this formula, because I know if you know your dE, then you can readily have this derived from the rate equation. That way you will not have to bother yourself memorizing so many formulas, because this is not the only formula that you will be encountering for now. So for a first order unimolecular type of reaction, of course elementary, you have now a formula that solves for the conversion as a function of time. So the key to this formula is this particular equation. The amount of A present after some time expressed in terms of conversion. So that's your Xa. So if we go back to our slide, oh, sorry. So if we go back to our slide, this is now the one that you have. So negative ln of 1 minus Xa, or quantity 1 minus Xa, is equal to Kt. Now there's a note in here written that the plot of ln 1 minus Xa, or ln of Ca over CaO versus T of the experimental data is tested. If the plot is not a straight line, another rate form is guessed and tested. What does this mean? The plot of ln, quantity 1 minus xa, or ln of Ca over Cao versus T of the provided experimental data is tested. If the plot is not a straight line, another rate form is guessed and tested. Now, anybody here in the class who can explain this, or who understands what this particular note in here on the slide means, or what's your understanding of this note here on the slide? What does it tell you to do? Anyone? What do you think is being asked of you to do? It's already telling you to test something. After you have guessed something, then you have to guess again if what you have tested does not conform to, saying here, if the plot is not a straight line, another rate form is guessed and tested. What does this mean? Or if anybody has an idea, what does it trying to tell us in this case? Anyone? Kenneth? Kenneth, what's your understanding of this, Kenneth? Do, do you understand what does this particular note is telling you to do? Abidejos? Okay, so what about Katrina? Do you have an idea, the slightest idea on what this particular note is telling you to do? Aliana?
Miss,
Yes?
base, ang gina namin, Miss, is lain nga rate form aside sa ln 1 minus xa or ang ln ca over cao.
Oh, so meaning naglain siya. Pero originally, ano ang pang-intindi mo, ang ginapaubra niya? What is it asking you to do? Katie, in the first place, you don't know that your experimental data uh, is still not fit for a first order reaction. But you have to understand that you need to do something first in order for you to know whether what you guessed is correct. So what will you do? What is it saying to you in your understanding? Hmm? Colleen, your classmates may need your understanding of this. Colleen?
Hello, Miss. I'm
Yes.
not sure, Miss,
Oh,
but
sige, so try lang.
um, siguro it asks you to plot lang man ang ln 1 minus xa versus t, or it can be ang ln ca over cao versus t para mabalaan mo if it's a straight line or not.
You will plot. So meaning the problem is going to provide you the XA, right?
Yes, Miss.
And the problem is also going to provide you the CA and the CAO. Is that it? Then you just plot the value of ln 1 minus XA or ln CA over CAA versus T. Is that what you mean?
Yes, Miss.
Okay. So I think Colleen understood it. The way I understood Colleen, she understood it. But let me show to you what Colleen is trying to say. I'm just asking that way. This will not be a monologue for 2 hours. There are problems, class, that will give you XA. Sorry. Wait. Why is it still eraser? I'm going to draw. Okay. There are problems that's going to give you a, what is this, a, let me just close this class and open again. Sorry for that. There are problems which are going to provide you conversion and time. What do you mean by that, Miss? Meaning the problem is going to give you something like this. There are values here of XA and time. Okay? This is the first scenario that you have. This could be one scenario. Another scenario is a problem will give you concentration and time. So of course you have pairs of data here of concentration and time. What the problem is, or what the note there is trying to tell you, just like what Colleen is trying to tell you, is that you're going to process ln of 1 minus xa. Remember that your, let me just admit this. Remember that your equation is negative ln 1 minus xa is equal to kt. And this is comparable to an equation of a line. So if I will place the negative sign on the other side of the equation, your equation of the line is something like this. And this entire thing now is your y. This is your x. And this is your m. If your provided data by the problem is conversion versus time, you will plot a new set of value, meaning you will not plot for the y, the raw value of xa, but rather you will plot ln of 1 minus xa against the time that is provided here. So what I mean is there's a need for you to have another raw here, and that would be the ln of 1 minus xa. The values that you have for xa here, you will need to use here in the argument of the ln. So 1 minus that value of xa and then take the ln. You will have new values here. These new values you will plot with t versus t because that would be now your y and x. If this data that you have for the problem is not a straight line with y-intercept right on the origin, then your guess that your reaction is a first order unimolecular type of reaction is wrong. You have to make another guess. That's just how it is. So your number one, your equation is to be a straight line, or rather your dots here, this one, this is one dot, this is another dot, this is another dot, that one, and this one. You will have 5 dots. They have to form a straight line whose y-intercept should be equal to 0 because we don't have a y-intercept in the case of this equation of a line. Because we know that our line, the equation of the line, is y mx plus b. In that case, we don't have a b here. So meaning you should conform to 2 conditions. Your set of points should be forming a straight line passing through the origin. Another scenario will be this one. So in this particular set of data that the problem provided you, you of course have to use a different equation because you know our equation then is ln Ca over Cao equal to Kt. So you will have an ln of Ca over Cao equal to negative Kt. Now, there is another form of writing this class. That way it would be much easier. And this is it. You know that for a division in the argument of the ln, that corresponds to 2 ln's. The ln of Ca minus the ln of Cao from your EMMA 101. And this would be equal to negative Kt. Now you have ln of Ca equal to negative Kt plus ln of Cao. Now you have an equation of a line here. As you could see, your line will have this as the wire, y. So this would be your y. This would be your m. This would be your x, and this entire thing will be your b, your y-intercept. Okay? So if this one does not have a y-intercept, this one has a y-intercept. So meaning you will have another row here, just like in the first scenario. You will process the raw CA value. You are to get the ln of CA for that. And then for each CA here, you will have an ln of CA here. That ln of CA you will plot against time. The slope should be negative k, and that would be the rate constant of your equation, and it should have a y-intercept equal to ln of CAO, meaning your condition for scenario number 2 is that your data points should be a straight line. These 4 data points should have or should make a straight line, not anymore passing through the origin, but rather intersecting the y-axis on the value ln of CAO. And CAO is most of the time provided in the problem. It's a constant. It's the initial concentration. So there's a way for you to plot the y-intercept. So it should have this y-intercept, and it should be a straight line. That's it. So if this 2 that was mentioned there in the note does not form a straight line, what you guess to be a unimolecular first order type of reaction is wrong. How did you test it? This is the manner of testing. So then since it's wrong, you have to make another guess. That's just it. You have to guess another rate law appropriate for a given set of data. If it's a straight line for that particular rate equation which you have processed, linearizing it into this form, equivalent to this form, then your guess for the rate law is correct for that particular type of reaction for the given set of data. Do you get it? Because this one, this particular type of example that I'm giving you here, deriving the equations, will be repeated on with the other orders of reaction that you will be guessing. And they are even much more complex. But I'm using this as the starting point to explain. That way you know that in the next guessing and testing that you will do, you will be using the same set of procedure with, of course, a different rate equation, a different formula for you to linearize and compare your experimental data with. Do you have any questions so far in here? Okay, so there's no more questions. So we will go back to our slide and go to the next type of reaction. Okay, so this is for our first order unimolecular type of reaction. So we have 2 sets of equations or formula. Now we go to the bimolecular type of reaction. So since it's bimolecular, then you have 2 moles of a species or 1 mole of 2 different species appearing on the left side of your equation. So you have now cases in here. So case 1. So case 1 is the oftenly encountered type of unimolecular, rather bimolecular type of second order reaction. So you have 2 different species here. So if you're going to write the rate law, that would be negative R sub A being equal to K C sub A, C sub B. The exponents or the powers in which the concentrations of A and B are raised is equal to 1 because the coefficients of A and B in the left side of your equation are all equal to 1. This K here, class, though I did not place the subscript of, should be K sub A because our rate was expressed in terms of A or species A. Notice that here you have 2 different derivatives replacing the negative R sub A. So it could be negative dCA dt or it could be negative dCB dt. Now, remember that this negative dCB dt is negative R sub B. And based on what we talked about regarding kinetics of homogeneous reaction, if this is 1:1, negative R sub A over 1 must be equal to negative R sub B over 1. And as such, they will all be equal. So it's all equal. Negative R sub A, negative dCA dt, and negative dCB dt. The right side should not be altered whatsoever because this is our rate law for this elementary bimolecular reaction. Okay, that's our case 1. So in this case, class, you could have the amounts of A and B reacted at any time are equal. The amounts of A and B reacted at any time are equal. Now, I have to ask this question. That way, I will be able to check whether you understand this one. Okay, what's your understanding of this for this case 1 for a second order bimolecular type of reaction? The amounts of A and B reacted at any time are equal. What's your understanding about this? Let me see. Um, Jabime, what's your understanding of the amounts of A and B reacted at any time being equal? Can you give?
Miss, good afternoon.
Yes, yes.
Kay sa pag-intindi ko, Miss, kaya sa equation na show ang concentration sang A is equal man sa concentration sang B or
This
ang
one.
sa rate sang A wala Miss equation. Ang dCA over dt, Miss,
Mm-mm.
equal siya, Miss, sa iya sang B, Miss.
Mm-mm. Is this the concentration or is this now talking of the rate of change of the concentration?
Rate, Miss, of
Okay,
change.
this is not the concentration. This is the rate of change of the concentration. Now, if the amounts of A and B reacted at any time are equal, I'd like to show, I'll have a new screen so you will see. If we have this particular, I'll go back to this equation that I have shown to you a while ago. Okay, right? And if I will distribute the CaO, so I will have CaO 1 minus CaO XA. And this is Ca. Of the 3 terms that you see appearing in this equation, Jabi May, which of the 3 represents the amount of A that has reacted after some time?
Ang Ca, Miss.
The amount of A that has reacted after some time. So you're telling me that would be the Ca on the left?
Ang ano gali, Miss, ang initial nga gin-multiply, Miss, sa XA.
So Iha, I'm just asking you in this particular formula now that I have 3 terms, right? So in the 3 terms that I have Ca, I have CaO, and I have CaOXe. So my simple question is, in the 3 terms that I have written here, which one represents the amount of A that has reacted after some time?
Ang CaO, Miss, nga CaOXa, Miss.
This is this one. So there. So you're telling me that this is the amount of A that has reacted after some time. Is that it?
Yes, Miss.
Okay, very good. So this is the amount of A that has reacted after some time. The C sub B that was written there on the right side of the rate law is C sub BO. Look here, 1 minus XB. Okay? I changed the initial concentration here in terms of A. I changed it to B, and I changed the XA to XB. I will also do the same thing. I will distribute it here, and I will have a CBO minus CBO XB. This is very fundamental in kinetics. That is why I'm asking you. So now you could see that they are the same in form. They only differ in subscript. The CBO XB is the amount of B that has reacted after some time. Just like CAO is the amount of A that has reacted after some time. Common sense tells us that if these amounts were subtracted from the original amounts present, that will give us the amounts left after some time for A and B. So in terms of the note that was written here, so my page now is very colorful. It says that the amounts of A and B that has reacted after some time should be equal for this bimolecular type of reaction. Because if you recall our discussion in the kinetics of homogeneous reaction, the amounts that have reacted for the species are based on the coefficients of the species that appear in your rate equation, or rather in your stoichiometric equation, not the rate equation. If you recall, our equation is A plus B forming the products. Okay? So the amount of A over that has reacted divided by its coefficient here is equal to the amount of B that has reacted divided by its coefficient here. So true to what we have learned in kinetics of homogeneous reaction, the previous set of slides, the amounts of A and B that has reacted after some time should be equal. And just like what Jabime is saying, this is the two amounts that is being referred to in that particular slide. Okay? Now I'll go back to our slide. You can interrupt me. Sorry, why did I stop? If you have any questions. So that's what it meant here. The amounts of A and B reacted at any time are equal because of the stoichiometric equation that tells it so. Now we'll move forward. You see this? Sorry. I have so many things in here that came from just one equations that were all equated to each other. And you should be able to understand that they all represent the same thing. You could see this negative R sub A. I will discuss this later, this part. This is, let me check. I will annotate so you will see. Okay. Hi. This is your, sorry class, why can't I annotate? This is your, I'll write here, if I will erase, I will close it, I cannot annotate anymore. This is your CA and this is your CB in the rate law. Now, this one, the M equal to CBO over CAO is the ratio of the initial concentration of B and A. And that's the representation of Levin's pill in our book, and the book that we are using, the major reference book. You can have any letters that you want here, but as long as you understand that that particular letter should represent the ratio of the initial concentration of B to A. Now, how about the CAO DXA DT? I will share new. How did CAO DXA DT came about? Okay, we'll have it. If you recall, you have RA being equal to negative DCA DT. And if you recall further that your CA is equal to CAO minus CAO XA. This is the expanded form because your CA is CAO times the quantity 1 minus XA. So ammonia siya. And you have here DT. Now, if you will perform differentiation here, we know from our calculus that the derivative of a constant, the CAO is a constant, is 0. That gives you the negative of the derivative of negative CAO dXA, which is simply CAO dXA dt. Okay, so that is why you see there in the PowerPoint presentation that we have replaced this one, the original negative dCA dt to CAO dXA dt. This one you should be able to use when you do your derivation later on. That way you can come up with a working equation that is appropriate for the data provided. Now, what do I mean with being appropriate for the data provided? Class, you cannot stick to this original derivative of the change in concentration versus time if the problem gives you conversion. So you have to have an alternative formula that deals with conversion. That's the purpose why Levenspiel changed the negative dCA dt to this expression. That way you can interchange at any time whichever of the two is applicable for your given set of experimental data. So now you understand that this negative dCA dt is just equivalent to this, again using this very fundamental equivalent of Ca. And that's your CaO times the quantity 1 minus Xa. So I'll go back to our slide and go back to this particular slide which has so many things in it. Now, this one was copied, so we're good with this now because you understand why your dCA dt was now written in this form. And what do you think happened here? You have K CaO squared, 1 minus Xa, and you have M minus Xa. What happened here? Okay, so I will go back to I will just show this one. That way you can do this derivation on your own. That way you will not need to memorize later on. Actually, there's no need for you to memorize because even in the board exam, you will have your handbook with you and you have a set of formula, tabulated formula for these different equations. What is important is you understand how the formula came about. It's not just the matter of memorizing the formula without understanding how the formula came about. So the question is, how did this came about after this one? Okay, how did this one came about after this? So let me try to show you this one because after that you will just have your math to help you get this and this. Okay, again, I'll go back to my whiteboard. Start with a new page. So you have on the right side RA equal to CaO dXA dt. And you have a K and you have a CaO minus CaO XA. And you have a CbO minus CbO XB. Okay, you have that. I'd like to get the CaO already. So I will have a K CaO and I have 1 minus XA and I have a CbO minus CbO XB. If you recall the one that I have shown to you a while ago, it has already the M. If you recall, there's already an M there. And this CaO is already squared. How is that? So we will have to make sure that we have here AM, or we will produce the M here in the two terms in here. So if you forgot, you just have to recall that M is equal to CbO CaO. And I need to see this in here. I need to see that in there. So what will I do? I need to see a CbO CaO. So what do I need to do? Anyone? I need to see this here. That way I can have an M based on the derivation that Levenspiel provided for us, or the formula that was provided for us. So what will I do? Anyone?
Substitute, miss.
Equate lang, miss.
Equate, wala ko anay obrahon. Paano ko ka-equate?
Bali, miss, miss, ma-multiply ka both sides ng CaO para mas
Ma-multiply ko
CbO.
both sides ng CaO. You mean I will multiply this side CaO?
Sa M is equals to CbO over CaO,
Or
miss.
will I place the CaO? What will I multiply, Marcel?
Bali, miss, sa M is equals to CbO over CaO, ma-multiply ka both sides ng CaO para ma-replace mo na din ng CbO.
What you mean ma-multiply ko both sides man? Kaya when you speak of multiplying both sides, then you're referring to the left and the right side of my equation, Marcel. What you mean I will multiply both sides?
I mean, miss, sa ano lang bala, miss, sa M is equals to CBO over CAO lang. Nga mo lang gin. Bali, i-equate ko lang ang CBO para ma-isolate ang M kag CAO.
Hindi ko kaintindi. Ilongguha. Anong obrahin ko?
Bali, ano, miss, CBO is equals to MCAO. Tapos, substitute ko na din ang CBO nga value sa equation.
I will have here, what do I place here, Marcel?
Bali, ano, miss, ang sa M, at dire lang gid sa M, bala, miss, sa kilid, sa
Dire?
pinaka-left side. Oo, nan.
Ang manok.
I-isolate ko lang gid ang CBO. Bali, mas CBO is equals to MCAO. Tapos, then, i-substitute ko na din ang value ka CBO sa equation.
CBO is equal to MCAO. Is that what you're trying to say?
Oo, miss.
Okay. Although you can do sige, lain naman style ni Marshall. I hope you understand what he's saying. So I will have a K CAO 1 minus XA. Then Marshall, I will have an M CAO. Is this what you're trying to say?
Yes, miss.
Okay. Sige. Amo na siya ha. MCAOXB. So I will have K. You will get this and place it here.
Yes, miss.
Okay. Sige. I will follow Sir Marshall. So you have here, and I will have an M minus an MXB. Let us go back to our slide. That's our slide, Marshall. Doesn't look similar, right? It's M minus XA. But you can make it similar. Of course, Marshall can make it similar, or anybody in the class. So tell me, the second parenthesis that should go with 1 minus XA should be an M minus XA. I'll go to our slide. Help me out here. So that's our thing there. What do we do? Anyone? What do we do? Come on. You can do it. What do we do here? Or is there another way of going about this? It's there actually in front of you. What will you do with this? Your problem is here. I want a different color. I want a blue or purple. This one is the problem. What do you do with this? Let me check. If you're still not hungry, we'll see. What do you do? Eugene, what will you do, Eugene? Do you have any suggestion, Eugene?
Wala pa, miss. Wait, ang good, miss.
Oh, sige. Eugene is going back to his drawing board or his scratching paper. Who else? Katrina, help us out here. What do we do with this?
Miss, ang last bila miss na slide, di ba M minus XB to siya miss no?
M minus XA iha.
XA.
Wala ta XB kay tungod nga naka-DXA ta. So kung mag-XB ka, hindi mo na siya ma-process karon imo DE kinalang para riho imo variable. So it's XA. M minus XA.
Pwede na. Suggestion. Ang idea ko lang, miss.
Sige.
What, pwede na siya, miss, magamit na xb is equal to 1 minus xa.
Hindi iha. Hindi gina pwede. Okay? Hindi na siya pwede.
Mm.
Okay. Okay. Sino pagid? Be? Sige. Come, think. Eugene nga. Balongan na Eugene. Si ano be? Si Joshua. Oh, Joshua.
Hello, miss.
Yes. Suggestion iho. What do I do?
Ang sa first problem is kaya na nakita ko nga ang CAO is XA is equals to CBO XA bala, miss. So can change lang, miss, ang ang CBO XA to CAO XA. Kaya do ka ang premise, miss, is ng equal bala, miss, ang amounts of equal of amount reacted of A and B, miss.
Di kung islan mo ni siya, ay sorry ha. Ano ganigin pa obra di sa ako ni Marcel man? Ano ganigin obra mo di Marcel, gin islan ko si amo na ni siya. So ginkuha ta amo na ni. So hindi ta ni pagsundon, Josh. Liwaton ta. What I'm trying to ask is para hindi na ta magliwat kay gintuduan na ta ni Sir Marcel nga amo niya dapat may lusot nin siya gapon. So ano? Ara man actually sa ari man di siya actually sa slide ang aton gamiton. Anong obrahon ta? Para hindi na ta magsulit balik to. Although this is another route, galing kay bago ko naman ni nakita nga route kay ti amo ning pasugdan ni Marcel. But we can still arrive at the same formula. Help me out or help your classmates out. Can you see, Josh? What are we supposed to do with this? Ini aton problema. Nan, ini. Or sino pagida akong hambal man? Si Emilio. Lime. Oh, Emilio.
Hello, Miss. Good afternoon.
Yes, afternoon. Oh, what do I do? Do you have any suggestion for us? Abe, kikakatatinong sa inyo per may ari ay. Si ining ano bala niyo, si do DJ ni siya, oh. Socrates. Suggestion, Socrates.
Yes, afternoon. Good pa ko, Miss.
Agating ka pa. Sige, kay kinala na tama. Yes.
Ano ba, miss? Ba siguro, miss, mabalik tato sa tong 1 minus XA.
Pabalikon mo, kuya.
Hindi, miss, bali, miss, do ka representation ka MXB, wala, miss, ako. Dira nga part nga para ma-correct siya. Or maybe.
Sakto lang gini mo, Sir Marcel po. Oh. Lain lang galing. Lain naman ni mo, yung galing nga ruta. Bago lang ni nga ruta, yung pagyan sa akon. Anyway, this is what we're going to do. Kaya kinalan ako mag-change ang link kay karon absenan ko to sa pihak. This is what you're going to do, ha? Para dasig. You have K, CAO squared. 1 minus XA. It seems like this M is our problem. So, para hindi ta napag-problemahon, balikon ta ni siya no? Okay, para hambal ni Josh Balato, CAO, XB. Han. Ti hambal ni Josh, ano gani hambal ni Josh kay misali kay na that your CAO XA is just your CBO XB based on what we have discussed as well. So I can change this. So I will have K CAO squared 1 minus XA M minus, I'll change it, XA CAO. C. So you will have K CAO squared 1 minus XA times M minus XA. That's the formula that Levin's field provided for you. Okay. I recall Katrina saying nga ining XB. So kinalagi ni siya ihakwaon kay hindi na siya ma-process ang DE mo kay ang imo di nga variable XA. So dapat XA na di tanan nga aman. So I will go back to my slide so I can point to you why should it all be uniform in terms of the variable that appears in the differential. It's because if you're going to take out this one here, you'll take it out from there. This one can now be processed using what? If you will solve this DE, what tool in integral calculus will you use? This one. Masolve na ta kaya mo na ni formula na ni ginatagya ho. Ti paano ni siya nga formula ay hanag amo ni. Siyempre, kinanlan ini nga DE, this DE should be evaluated. Or you need to solve the DE. What tool in integral calculus will you use? That way, this DE can produce these formulas. They are all equated. What tool in integral calculus? Trisha, Charmaine, what tool in integral calculus will we use? Gabasi, nag-invent naman ko name, dali lang. Oh, Trisha, Charmaine, tsakto akong complete na name. What tool in integral calculus will you use? That way, this one can provide us the formula that you're seeing below. Of course, this is not the raw answer. There are subsequent derivations to come up with this particular relationship. What would that be? Trisha, are you there?
Yes, Miss.
What do you think? What do you think? Oh, yan lang. Ang wala ko pa nabatian tingog. Si Antoinette, what tool in integral calculus will help you solve the formulas that you are seeing below? All of these are all equal. Equal, 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 equal. As long as m is not equal to 1.
Ano, Miss? Afternoon.
Yes,
What
afternoon. Yes.
Equal sila.
O, equal ni sila tanan iha. So, pero before ka makaamo sini nga formula, may math ka anay nga itakol diri. Ang DE mo nga iniyo, imo ni siya na isolbon. So, what process in differential calculus and integral calculus will lead you to the formulas that you have here? This has to be answered first. What particular process is that?
Ano, Miss? Ang uniform DE, Miss.
Uniform DE. Sino inyo DE? Ako, hindi. Hindi ako?
Hindi, Miss.
Ah, okay. Anong uniform DE man?
Sorry, Miss. Iyon ako.
Pagod ako sa uniform DE. Ano nga mga uniform DE?
Dumara na, Miss. Dumara man na, Miss.
There's no such thing of a uniform DE. Oh, sige Oh, sige na amnesia na si Antoinette. O nagkaladula na nga ako ni estudyante. 60 na lang kamo. Ma-sit work ko guro ay. Hindi na sila nagkalalad to. Anyway, Aliana, help us out here. What do we do, Aliana? What do we do with this DE?
Hindi ko sure, Miss.
Sige lang, ano lang. Paano mo ni sulbo ng DE niyo? Ti karon kung tagaan ka mo ni, ma-memorize ka mo yung formula? Or pangitao nyo doon sa inyo, handbook ang formula? Kay, do ka man na nga hindi ka mo kabalo mag-solve DE. Ano ni pag-solve ang DE? Man, sino naman ang way ko mabatian man? Meryl Castillo, Meryl Lynch.
Good afternoon.
Yes.
Ang DE, remember ko, Miss, is ano lang, Miss, sabihin, ang gani, separable.
Correct. Correct. You do separation of variables. After you have done separation of variables, what will you do next? That's my last question. I need to transfer to a different link. What will you do next? you separate variables, meaning this 1 minus XA and this M minus XA should be transferred here. The rest on the right side. What would you do next? Nag-separate ka na variables. Then ano dason?
Integrate.
Integrate. Who said that? Who said that? Integrate. Did not see. Who said that? See? Who was that? Si Renzo? Si Marcel?
Si Sok, Miss.
Ah, si Socrates. O, ara na siya. Nag-work na siya ang iyang mind. Now, Renzo, we have done already separation of variables. How do I integrate? Renzo. Renzo. How do I integrate? Ah, wala tao ang balay. Di na si Renzo. Hari man si Renzo ho. Renzo. Hala, natulugan siguro. Renzo. Oh. Wala na ko sang ilawagon. Kaya nalawag ko na tanan. Raymond! Raymond! What do we do, Raymond? You have separated variables. How do you integrate, Raymond? Raymond. Joshua. Para tapos na, Josh. How do I integrate, Josh?
Ano, miss, hindi ko sure, miss. Kaya ang sa dalawang bala, miss, sa one.
Oo,
Diba
sa dalo.
dxa
Oo.
over 1 minus xa, mxa, m minus xa, miss.
Oo.
T equals to k cao dt, miss.
Oo, you're right. Very good. So, ano mo na pag-process ang integral?
Oh, wala ginapalibugan pala sa miss.
Ah, ginapalibugan.
Kay polynomial siya, miss. Ma-polynomial siya sa dalawang
Rational expression siya.
Rational. Rational, miss.
Okay, sige ah. I will place in Canvas. Yes?
Ng partial fractions. Miss.
Ay, salamat, Eugene. Ikaw na, Eugene?
Oh, miss.
You will use method of partial fractions. Okay, I'm sure Miss Nite discussed that to you. Okay, if I'm not mistaken, I seated in her class in which she is discussing method of partial fractions. So you are to use method of partial fraction to evaluate the DE that Joshua just orally mentioned a while ago. So to come up with this, okay? Now, I will give you assignments on how these particular formulas are derived. I will just have it posted in Canvas para ma-exercise ka mo mag-derive kag mag-review sa inyo differential equation kag integral calculus because it's very important here in interpretation of batch reactor data, especially with integral method of analysis. Okay, I will stop sharing here for now, class. I need to go to the new link that I gave you because I might be marked absent already in that link. Okay, I will end it here. You use the second link that I have provided in our GC. You can, okay, I will end now. I'll see you there.